So this is going to be part number 5 of collective communications in MPI. And welcome back. So of course we're going to continue from where we left off, and we already briefly talked about this MPI all to all. Now MPI all to all is an extension of MPI all gather to the case where each MPI process sends distinct data to each of the receivers. The jth block sent from MPI process I is received by MPI process J and is placed in the ith block of receive buffer. So you have sort of a symmetry. A jth block from process I is going to be in process J placed in the ith block. So it's going to be like reversed. So type signature associated to set type send count at an MPI process must be equal to type signature associated with receive count and receive type at the MPI process and the other MPI process. This implies that the size of the data that must be equal to the size of received pairwise between those processes. Okay, these we already know. We're not going to talk about this one. We already know what it means. And then we have an in-place option in case when we want to use it as send buffer. For all processes. So boom, let's go to MPI all to all. Let's take a look. Of course, Final Cut Pro is also rendering other episodes right now. So MPI all, what was it called? All to all. Let's see. Okay, these things are the same more or less. Okay, now everybody needs to allocate proper space for the buffers. So that is the send buffer with the size. And everybody needs to initialize that send buffer uniquely. In this case, we have I plus the rank. So we're going to have, for example, the 0 is going to have 0 plus 0. That's 0. And then everything is going to be like, it's a combination of the loop sort of counter and the rank of the processes. I'm not going to continue on counting these things. And then we have receive buffer that you see that, again, not only process 0, but every other process needs to allocate the proper receive buffer for that. Then we have for complexity, for one more level of complexity, we're going to have C-style strings. This time we have a two-dimensional array because we need to have size of those arrays, let's say. If we are running with 8 processes, it's going to be 8 of these C-style strings with a size of 10. So that is the difference. And every processor needs to uniquely sort of fill up all the information inside the strings. We are using a combination of %d, a combination of rank and a loop counter, again, similar to the send buffer, combination of the root counter and the rank. MPI all to all. Notice that we are using MPI com world. Again, this is an intra communicator scenario. We pass in all the proper arguments, send buffer, receive buffer, the counts, the types, the counts, the types. And since we have MPI in place for the send buffer here, for all the processes, again, this is not only for process 0, that is why we don't have an if statement here, because everybody is gonna send and receive. So this is that complete mishmash. So that is why the proper receive buffer, the receive string, needs to be populated with the information we had in send string, which we sort of populated earlier with this call here. Okay, and then in the end, of course, since it's a mishmash, we presented the results in process 0, process 1, and process 2. Of course, you could also continue with other processes, but it's going to be messy. We're going to free the resources finally. So MPI CC MPI all to all. Let's see, and MPI run. So you see that root process has 0 through 7, and then we have the receive string. You see we have 2 combinations of rank and the loop counter. And process number 1 is going to have 1, 2, 3, 4, 5, 6, 7, 8. You see that the reason that these are different is because that you had that combination of I and the rank. And for process number 2 is going to be 2, 3, 4, 5, 6, 7, 8, and 9. Again, you're gonna have also different sort of numbers associated here because we are using a combination of rank and the loop counter. So that's a very beautiful example here. And then if we have the case of intercommunicator, we have a proper example for that, MPI all-to-all inter. So let's take a look at that. All-to-all inter. So this is exactly the same scenario, but the only difference is that we're going to have an intercommunicator, and then our buffers are going to be having the size of world size. And here again, we are using a combination of I and world rank, but the receive buffer is different. So send buffer has the world size but the receive buffer for processes in group A is going to have the size of processes in group B, and for processes in group B is going to have the same size as processes in group A. And then you call MPI all to all, and this time you don't pass MPI com world, but you pass intercommunicator. And then processes in group 0, not in group 0, but in group A, are going to print their results. Notice that for less complexity, we only use that integers. We didn't use the C style strings. And then all the other processes in group B, they're going to print their own results. So this thing is going to be very messy. So this time I'm going to try to run it with 4 processes maybe. MPI run minus NP4. So you see that proc 0 and 1, they have information from group B, which is 2, 3, 3, and 4. And proc 2 and 3, they have information from processes 0 and 1, which are group A, which is 0 and 1 and 1 and 2. So you see beautifully. If I was using 8, this was probably a little bit more messier. So it was harder for you to follow that really these first 4 processes are in group A and the second 4 processes are in group B. And you can see the counters, how they're moving. Okay, so the next thing on the line is all-to-all V, similar to, let's say, gather and all gather. They have a V version. You already know the drill, that it gives you the flexibility that you have. In case of all-to-all, it gives you the flexibility that you have an array for send counts, an array for send displacements, an array for receive counts, an array for receive displacements. So that's the only difference with the other. I mentioned it also. I circled them so that you know that these things are now not only one element, they're an array of elements now. So these things are going to be exactly similar to all. So we're going to jump in to see only the examples. MPI all v.c. Everything is the same, but we're going to have a shit ton of other or extra variables. We have receive displacements with the size of the whole, let's say, communicator. We have send displacements. This is for the integer. Receive counts. This is for the integer. Send counts. This is for the integer. All these 4 are for the integer buffers. And for complexity, we added also stuff about the strings. So we have a string displacements for R, this is receive, S for the send, receive string counts, and send string counts. We put the proper values because displacements are going to be based on their rank, and counts are going to be 1 for the integer. They're going to be 10 for the C style strings because of the same reason that we said that this thing has the size of 10. And yeah, did I pass here? I did pass here, yeah. We need to also initialize them, properly initialize them or uniquely initialize them in all processes, both the strings and integers. And then you call MPI all-to-all V. You pass in all the necessary elements here, but notice that this time you're not having a count and a type, but instead you are having an array of displacements for send, an array of displacements for receive. It gives you more flexibility. And then you're using MPI com world because this is an intra communicator scenario. And since we want to use in place, we need to take care of the receive buffer for every sort of rank. We need to properly populate it with the string that we already populated. And we call MPI all-to-all V with the send buffer as MPI in place. So this is the only difference. And then again, for example, for the sake of an example, we have processes 0, processes 1, and processes 2 to show their own results, both the strings and their integer buffers. So MPI CC, MPI all to all v.c, and let's go with MPI, MPI run. This is the same pattern sort of we have seen, but this time we are using with all to all v, which gives us flexibility to have array of displacements, array of counts for send and receive. We pass in here. Finally, this is the most general case, which is all to all w. Not only it gives you the send count array, send displacement array, receive count array, receive displacement array, but it also gives you array of types. It also gives you send and receive types of arrays. Take a look at here, send types. It's an array this time. It's not only a single type. And also receive type is not a single sort of data type, but it's an array of data types. So this is similar to the case that, if you remember, that we had for data types, that we had that struct, MPI type struct, that basically gave off all the flexibility in the world, This MPI all to all v also, or v in German, but w is going to give you all the flexibility in the world. So you see that this is an array, and the data types are also an array. Again, semantics are going to be all the same, but we have more flexibility. That's the only difference. So we're going to jump. So this is the global reduction operations. So I'm going to finish these two examples, and I'm going to wrap up this episode. So let's take a look at MPI all to all w. Okay. So here, send buffer is going to be of size, all the processes. Everybody needs to allocate proper size. Then you're going to populate it sort of uniquely with a combination of the loop counter and also the rank. You need to allocate proper space with the malloc call. And then for complexity, again, we add a CS-style string. Again, we are using two-dimensional array. Size of them we need. Size is actually the size of the number of processes that we are using. And then every sort of CS-style string is going to have 10 slots of characters. Again, we are using a combination of rank and the loop sort of, let's say, counter. And a receive string is going to have the proper size. Then we are going to have a shit ton of other let's say, variables. Receive send displacements, receive send counts. We're going to have data types populated with size. And we're going to have one set for the integer buffer, one set for the string, the C-style string buffer. We're going to give all of those extra variables proper sort of displacements or sizing, depending on their rank for the displacements. Receive and send counts is going to be 1 because the integers are going to be 1, which are transferred. Types are going to be MPI int. And for the string, we are using for the counts 10 because of that buffer. And then the displacements are going to be according to their rank. And the types are going to be always MPI character. Then we call MPI all to all w. Since we are sort of matching everything with what we have in MPI all to all v and MPI all to all, then the output that we see should be exactly the same as all those other outputs. And since we want to use MPI in place, then again, we're going to use this one. And notice that we are using MPI com-world as a communicator because we are taking a look at the intra communicator scenario. And then again, the same sort of output from process 0, process 1, and process 2. So let's go and do MPI CC MPI all to all w and MPI run. You see that these outputs are exactly the same as the outputs with sort of MPI all to all w. The reason for that is we have used the same type of character for the C-style strings and the same type of integer for all of the integer buffers. but you have all the flexibility in the world. So in this simple example, I just wanted to have a sort of ground that I can check my results that they are the same for all MPI all to all, MPI all to all V, and MPI all to all W. So the next scenario is going to be the intercommunicator scenario. That's the last scenario we're going to take a look at. It's MPI all to all W and inter. Again, this section is for the intercommunicator, and then we're going to have world size for the send buffer. We populate it. And receive buffer, displacements, and counts, they're all are going to be null pointers. And the reason for that is once you're talking about intercommunicator, the size that you need to allocate is going to be different depending on what is the size of group B and what is the size of group A. So for group A, these are called as 0. The size is going to be the same size as the processes in group B, which is the world size minus local size. And for group B, which is after this else statement, the size is going to be the same size as the processes in group A. That is why we have a local size here. As we mentioned before, this two sizes, if you are using even number of sort of processes, 10, 8, 6, I don't know, 12, these two are going to be the same. But if you're using even sort of numbers, then these two are going to be different in one. That's the significance here. Then you need to have the receive buffer allocated with malloc. You have a lot of malloc calls here. You need to be very, very careful because in the end you need to free all these things. So that is why we have a trillion of free operations here or functions. And then you properly need to allocate the displacements based on their ranks and the counts based on their sort of how many counts. This is, in this case, we're going to send one integer. And again, just like always, because this thing is very complicated, I removed the C style string here because it's going to make it like very, very complicated. We already basically left us alone with the integer buffer. For group B, you also need to do the same, allocate with the proper sizing of group A, and then you need to do the proper displacement and the proper sizing of counts. And then finally, you need to, this is super important. We passed in a count here because we didn't know what is going to be the send type, because the count is going to be different if we use an even number of processes. So we generated the count, we didn't initialize it, but inside each of these groups, we populated it with the proper sizing. So all the processes in group A, they're going to have this count for them is going to be the size of processes in group B. And for all processes in group B, which is here, this count is going to be the size of group A. So that's the significance here. And then you need to basically populate those types. The count is going to be different. Think about it concurrently. The count can be different if you're using an odd number of processes here. It's going to be integer for both send and receive, but you have the option to have different types, different displacements, different counts. And then we call MPI all to all W, and notice that the only difference with all to all W that in previous example we saw is that we are not using MPI com world, but we are using intercommunicator. And then finally, all the processes in group A, they're going to print their own results. And all the processes I'm sorry. I think this is because I copied these examples, this comment, you need to ignore that. It says cause we have MPI in place for our char star strings. We don't have any char star strings here because I used the same sort of template. I wrote one example and then I used it. Okay, so all the processes in group A, they're going to print their own results. And all the processes in group B, they're going to print their own results. So let's go with MPI CC, MPI all to all, W, the intercommunicator case. And let's run it with 8 processes, or maybe 4 processes is easier to digest. And you see again process in group A, you have information from 2, 3, 3, and 4 from group B. And in group B, you have information from group A, which is 0, 1, and 1 and 2. Here we are only working with sort of the integer buffer, not with the C style string. So there we go. We're going to stop here. We're not going to start talking about reduce operations. That's going to be the subject of the next episode. But so we have finished basically all the let's say all the blocking collective communications, excluding those reduced operations. The reason is because those reduced operations have more significance or more importance to them. That's why I wanted to have a separate episode for them. So I hope you learned something from this video, and hope to see you in the next part, not in the next actually topic or chapter. It's going to be the next part of collective communication.